Can everyone hear me?
Yep, can hear you.
Excellent.
Yep.
Excellent. Thank you very much for that, Liz. And thank you very much for inviting me to present in this the opening of the Datathon. So the previous speakers, I guess, have talked fairly generally about data science in health and medicine, and then Vicky at the end there was touching on imaging. So I'm just going to focus on imaging as a specific application and hopefully show that it's a fairly rich field with a lot of opportunities for data scientists. So first, I just want to take you all back to 1895, and this is the very first human radiological image created, which was created by Wilhelm Röntgen of his wife's hand. And at the time, this was the net sum of radiological data in the world, and a sample of one. And we might look at that image and say there's maybe about 10 features that we could extract, which are representative of a compressed tissue in 2 dimensions. It's some function of the composition of that tissue. And this is fairly easy to be interpreted by a radiologist. So if we skip forward 135 years or so, then this is a sort of data set that is facing clinicians now. In fact, this is only a sample of it because each of these image sets is a 3-dimensional set and we're only showing a 2-dimensional image. So here we have combinations of CT, computer tomography data, MRI data using different MRI sequences to obtain different bits of information about this patient's brain, as well as PET, positron emission tomography imaging using different traces. So traces identify different functions in the brain, and also a dynamic PET image. So each of these could also be varying in time. So we no longer have just the one patient. We may have a few hundred if this was from a clinical trial. We may have a few 100,000 if this is being extracted from the hospital's information system. And collectively, there might be 1 billion features throughout that data set, and representing a whole range of characteristics of this patient and the composition of their brain and their tissues and what their brain is actually doing. And the concept that this could be interpreted by a radiologist, even the most clever out there, is just not conceivable. If we assume that most people can manage about 10 to 20 features simultaneously, then they're not going to be able to trawl through this data set for features that may actually vary between different image types and over time. So imaging provides a very rich amount of data that we can trawl through in order to obtain information. And this little figure just comparing imaging to other ways of getting precise information on patients, and that's by taking a biopsy of their tissue or taking a sample of their blood, so a liquid biopsy. And so we're just looking here at how specific each of those techniques is, how often they can be performed, and then how accurately they give information in the spatial domain. So a solid biopsy might be very, very specific and give us genetic information about a sample of tissue, but it can't be performed frequently, and it's only for one very small location in the patient's body. A liquid biopsy will give us, can be done fairly frequently. The specificity of the information is now a bit limited because it can come from anywhere in the body, and the spatial localization is very limited because this blood is a sample of all tissues in the body essentially. So imaging can actually bridge a lot of the gaps here and increase the scope of what we can do in characterizing an individual patient. So this is just sort of illustrating the way that imaging can be used. So we're assessing a patient using different methods. So we might use PET imaging, CT or MRI or other methods. We can combine that with genetic, metabolomic, phenomic information about that patient to create a very rich data set. So we can look at extracting features from that data. So in the radiological world, we call this feature extraction the process of radiomics extraction. And we can use those features in a machine learning model to predict outcomes for those patients, for example. Or we might also use a neural network approach to extract unsupervised features from those images. And then from that process, hopefully we'll end up with a model that can be translated to understanding future patients better. So to using their information to categorise their disease, to categorise their own tissues, or to make prognoses about how they're going to respond to a specific treatment. And we might also gain some understanding about how their tissues behave. So how the cancer behaves, for example, why it responds to a certain treatment, whereas the next patient, they may not respond. And so the imaging domain in biomedicine spans everything from pathology, so looking at imaging of cells on tissue slides under microscopes, through the preclinical world, which is where we're testing drugs and interventions on animals, and right into the clinical world where we're using these technologies directly on patients. And by extracting these features, by doing the data analytics on these images and these patients' outcomes, there's a whole raft of tools that we can extract from that process, such as diagnostics tools, so screening mechanisms, decision support. So Vicky just talked about the way we can use these models to assist clinicians in making their decisions, all the way through to classification of disease, predicting how disease might respond, and even understanding it. From a global perspective, medical imaging is a huge growth area, so currently growing at about 6% per annum, which is being driven by an increase in the prevalence of chronic disease as the population ages, but especially the uptake of medical imaging in emerging economies, which is a huge driver in the market. And the analytics that's being done on these images is actually just increasing that growth even more. So now we're not just looking at these images and making decisions, we're deriving models on them, and that's actually increasing the demand for imaging so that those models can be implemented. So this is a cyclic process, and that's increasing the growth in the medical image field. Just results from the last decade in the US market. In the medical imaging field, data analytics has led to the largest number of new companies with the largest transaction volume and value of share transactions, and those companies have had the largest average revenue. So this is actually a huge market driver. And I just want to give one example of how this process occurs and what sort of information it can yield. So I particularly work in the cancer space, and one of the huge issues in treating cancer patients is when their disease metastasizes, so spreads away from where it started. And what happens is that disease starts to evolve, its genetic characteristics start to change, and it actually starts to become resistant to the treatments we're trying to apply to it. So on the left here is a patient who has had what's called a sodium fluoride PET scan, and just delineated in red each of the metastases in that patient at one time point. So that patient comes back a month later and is rescanned, and as you can see, their disease has increased considerably and spread throughout their body much more extensively. So this is a patient with advanced disease who's likely to die from this particular illness. So a group that we work with in Wisconsin developed this method for registering these two image data sets based on the bony anatomy of the patients, and then that information can be used to align these individual metastases between the two images, so that we can actually see which of these are responding to treatment and which are not. And we can look at the ones that are not responding and take a solid biopsy of them and get much more specific information about those lesions to understand what is it that's driving the resistance to treatment. And from this we get a map of those lesions that are responding and those that are not. So what we really want to know is, what is it in this original image at the first time point that predicts that this is going to happen to this patient and try to intervene before that disease spread has happened. So it's interesting that the previous couple of talks have mentioned how important infrastructure and governance around data is, and it's certainly the case in our field. The tools are out there. So Vicky just talked about AWS's tools, and so access to those algorithms and the resources to do this modelling are no longer a barrier to this work. One of the main barriers is actually having the data in the first place and having it have high quality and to be able to be used. So what we really want is to be able to adapt those tools, those algorithms, to the particular problems that we're interested in. If you're a data scientist at the moment looking for a field to go into, this is certainly a great field, and some domain knowledge is an advantage, particularly if we know what types of algorithms can be applied in imaging, but certainly not essential because we tend to work in very large multidisciplinary teams where that expertise is already present. We want creative approaches to investigating this data, although I say very highly self-critical. What I mean by that is there's a lot to lose if we get these models wrong. So these are patients' lives that depend on these models. Typically we're after high sensitivity at the expense of specificity, because we don't want those false negatives slipping through, because they're the ones that end up being lethal. And we also want a learning path. And what I've got showing in this figure is starting off with a data source, which might be from a clinical trial, which passes through analysis to development of an application, to a deployed application. And this process sort of used to work maybe a decade ago, but this is a very rapidly evolving space, and this doesn't necessarily work anymore. What we really want is a cycle where we're producing these analyses, we're externally validating to make sure that they actually apply outside the space they were developed, to obtain that application and create new data, which then feeds back to that analysis process and is used to inform the application again. So it's a new way of looking at the use of data and how it needs to evolve and learn over time and adapt to what's happening to patients and how they're responding. So as Liz mentioned, we've been creating a centre called the Australian Centre for Quantitative Imaging, based here in Perth, where we're looking at implementing these techniques in different settings. So what ACCI will do is do new independent research into these algorithms and how they're used. We will support researchers who want to incorporate imaging analytics into their work to get better use of their data and better insights into their data. It'll be a training and education hub so that clinicians can become aware of data science and AI methods and how they can be used in their clinics and how they can be applied, but also a training hub for data scientists working in this area. It'll also be a centre for examining how we can deploy these particular algorithms and methods. So how do we clinically implement them, including their costing? And then also it'll be an innovation and commercialisation hub so that companies can actually come in and be embedded in this environment and learn on the data. So if you're interested, please go to acci.org and you can also just add a request there to provide your information and let us know you're interested. So once again, just very much thank the Data Science Hub team and AWS for inviting me and supporting this initiative, which is really fantastic, and I look forward to seeing all the results that you generate.